Hi, so we're back to continue on with chapter 3. So we're talking about the development of quantum mechanics. So I'll go back to our PowerPoint. And we were going to look at this example. I'm not sure how to move that. Oh, there we go. Okay, so the example is going to be, let's just look back at where we were. So we were on this slide when I last talked to you, and this is a slide that shows you when an electron's in the hydrogen atom, it has energy relative to an energy of 0. So the energy of 0 would be when the electron is completely removed and it's no longer close enough to even see the proton that is the nucleus. And so that's the very top. That would be an n of infinity, a quantum number of infinity. And when it's in its ground state, it's at this bottom line, the purple. So it has negative energy relative to 0, which means there's an attraction between the electron and the proton. And so each of these arrows was representing how much energy it would take, for example, for the electron to go on the very far left from the ground state up to the first excited state, or the second line up to the second excited state. So you have then in the middle, a situation where you start in the n equals 2 state and you go up to the 3, the 4, the 5, and those would all be absorption. So it would take a photon, you'd have to absorb energy for the electron to go higher in energy. And then on the right-hand side, it's showing you those same transitions. But if you're returning back to the ground state or returning to a lower state, that means you're giving off energy in the form of a photon. So we want to look at this problem. So what's the energy and the wavelength of the line in the spectrum of hydrogen that represents the movement of an electron from a Bohr orbit with n equals 4 to n equals 6? And what part of the electromagnetic spectrum do we find this? If I asked you something about the electromagnetic spectrum regions, I would give you that spectrum. You don't have to memorize that. So we're going to use the equation for the hydrogen atoms energy differences, and they're separated in energy, and they're proportional to 1 over an integer. So in the case, we're going to say that n equals 4, so n1 equals 4, and it comes to rest at n equals 6. So 1 over 4 squared minus 1 over 6 squared times the Rydberg constant in units of joules. You multiply those, you end up with an energy separation between the 4th and the 6th state, and it's 7.566 times 10 to the minus 20. Pretty tiny number when you're talking about one little electron. If you were talking about like a mole of electrons, that'd be a different question. But this is just in one atom, how far apart are those two states? So the energy difference is positive. That means that you have to absorb a photon for the electron to go from 4 to 6. So it's going up in energy. When you look back at this picture, it would be one of these on the left-hand side. And now if we want to get the wavelength, we know that the energy of the photon that would be absorbed has to be equal to the difference in the energy of those two states. So the delta E that we just calculated has to be equal to hc over lambda, because that's the energy of a photon. And so we just rearrange that and solve for lambda in meters. And then you could look on the electromagnetic spectrum that I'd give you, and that would show you that it's in the infrared. So it's IR radiation. So the limitations of the Bohr model, that's one thing you want to take from this, is that the Bohr model only works for hydrogen or hydrogen-like atoms. So atoms that only have one electron, or ions that only have one electron. So hydrogen atom, helium plus 1 cation, lithium plus 2 cation. And so it doesn't work even when you get to 2 electrons. So that's because it doesn't take into account that electrons interact with each other. It only takes into account that electrons are attracted to the nucleus, but they're also repelled by each other. So the model was severely flawed since it was still based on the classical mechanics motion of precise orbitals. So using Bohr's model, where you think about electrons as circling the nucleus in little orbits like planets around the sun, you won't get a theory that can explain all of the atoms in the periodic table. So the Bohr model does introduce several important features of all models used to describe the description of electrons in an atom. So even though it's not a model that stuck, it was a model that we learned something from. So the energies of the electrons in an atom are quantized, described by quantum numbers. So those n's are quantum numbers, integer numbers having only specific allowed values, and they're used to characterize the arrangements of electrons in an atom. So an atom's electrons can't just take on any amount of energy. They're limited by quantum numbers, and therefore they have discrete energies. An electron's energy increases with increasing distance from the nucleus. So that's what our picture showed us. As you get further from the nucleus, you're pulling the electron to a higher energy state. In this case, you could pull it all the way to the point where it's separated from the proton, but you're going to less negative numbers, so the energy is getting bigger. The discrete energies are the lines in the spectrum of the elements result from quantized electronic energies, and that's the big takeaway from the Bohr model. So Bohr did win a Nobel Prize in physics for his contributions to quantum mechanics. Became clear to most physicists at that time that the classical theories that work so well for the big things like baseballs and people were flawed, and that they couldn't be extended down to atoms and molecules. And that a proper model of quantum mechanics was later developed to supersede classical mechanics. So Bohr's model took us a step closer. We understood that there were quantum numbers necessary and discrete energies, but it wasn't a complete theory, and we moved on to quantum mechanics. So quantum mechanics, it extends the concept of wave-particle duality that we saw with the photoelectric effect and electromagnetic radiation to matter as well. So if a wave, light, electromagnetic radiation can also have particle nature, the postulate was, well, maybe a particle like an electron can have wave nature. And so we can understand the general idea of quantum mechanical description of electrons in an atom. That's one of our goals, to understand that. List and describe traits of the 4 quantum numbers that form the basis for the completely specification of a state of an electron in an atom. So that will take us the majority of the rest of this discussion. So development of quantum mechanics. Particles and waves are very different phenomena in the macroscopic realm. But by the 1920s, so quantum mechanics was completely developed by 1926. The photoelectric effect was developed in 1905. So you can kind of think about the time it took for this theory to be developed. By the 1920s, it became increasingly clear that very small pieces of matter follow a different set of rules than those that we observe for large objects. The unquestionable separation of waves and particles was no longer the case for the microscopic world. So having that dual nature is really the fundamental concept in quantum mechanics. And this is just a pattern to remind you of what it means to have wave nature. So this shows you the interference pattern of waves in water. And now we're saying that electrons themselves have some sort of wave nature and an interference pattern. So I think before we start into the development of quantum mechanics any further, I think it's important to realize that quantum mechanics starts with a set of postulates, and it just works. And no one really understands what it means for a particle to be a particle in a wave. And so some people find that that must mean quantum mechanics is flawed. But the interesting thing is quantum mechanics is the most validated theory in physics. So every time you try to use quantum mechanics to solve a new problem, it works. So that idea that we can't really understand conceptually what it's telling us shouldn't override the fact that it's a very, very useful theory, very, very well validated. So Louis de Broglie was one of the pioneers. So he started out and said, if electromagnetic radiation can have particle character, can electrons and other particles have wave-like nature? And so we start with that idea. and he extended that to resolve the photoelectric effect. Just wait, yeah, he just extended what Einstein said about light to particles. So de Broglie, he had to come up with an equation. So if you say a particle has wave nature, well, what's its wave nature? So he came up with this equation that says the wavelength of a particle. So now this isn't electromagnetic radiation. It's an electron or a baseball. It's a particle. So the wavelength is equal to Planck's constant over momentum. Momentum is P, which is mass times velocity. So that's not frequency in the denominator either. So the wavelength of a particle is equal to a very small constant, Planck's constant, divided by the momentum, mv. So the de Broglie wavelength is a characteristic of particles, not of electromagnetic radiation. So Bohr had postulated the electron as being a particle orbiting the nucleus in quantized orbits. De Broglie argued that Bohr's assumption of quantization can be explained if the electron is considered a circular standing wave. Only an integer number of wavelengths can fit exactly within the orbit. And that's what this picture is showing, that if that wave is to fit in that circle around the nucleus, so the dot in the middle would be the nucleus of your atom, then it has to have a certain wavelength so that at that radius, you don't have any quarter waves. You have basically the wave comes right back to where it started. So for a circular orbit of radius r, the circumference is 2 pi r. And so de Broglie's condition is that 2 pi r has to equal n times the wavelength. So you have to fit into that circle an integer number of wavelengths. And so Davison and Gurman demonstrated that electrons can exhibit wave-like behavior by looking at the fact that electrons do have interference patterns with each other, just like photons did. They have showed that electrons traveling through a regular atomic pattern in a crystal produced an interference pattern, and the interference pattern is strikingly similar to the interference patterns for light. So this is just a picture showing that. So we saw this picture earlier when they were talking about light. I don't think I'll go all the way back, but this looks very, very similar. But this shows you that that wave nature is making it so electrons interfere with their own wavelength. So it appears that while electrons are small localized particles, their motion does not follow the equations of motion implied by classical mechanics. So Newton's equations of motion, which up to this time had been used to solve the motion of all particles, don't work when you're talking about small things like electrons. Instead, some type of wave equation governs a probability distribution for an electron's motion. And so the wave-particle duality first observed with photons is actually a fundamental behavior intrinsic to all quantum particles. So at the same time, Heisenberg was starting to think about these ideas. And so he and de Broglie kind of had a complementary way to look at the wave nature. And Heisenberg determined that there's a fundamental limit to how accurately one can measure both a particle's position and its momentum at the same time. Essentially, that's the same thing as saying a particle has this wave nature to it. Not being able to know where a particle is exactly gives you kind of a fuzzy look at it rather than an absolute look at it. And so it's a similar concept, Heisenberg's uncertainty principle and de Broglie's wavelength. So the more accurately we measure the momentum, the less accurately we can determine its position at that time, and vice versa. So Heisenberg's uncertainty principle, it is fundamentally impossible to determine simultaneously and exactly both the momentum and the position of a particle. And so put into an equation, delta x is the uncertainty in where the particle is, delta px is the uncertainty in its momentum in that same dimension. That's always going to be greater than or equal to h bar over 2. The very best you can do is it's equal to h bar over 2, but then when you design an experiment, that will always just be a limit, and you're probably going to have uncertainty that's greater than that. So the quantum mechanical model of an atom. So now when we talk about an atom, we're not just talking about one particle with one wavelength. So Schrodinger extended de Broglie's work by incorporating the de Broglie relation into a wave equation. Today, this equation is known as Schrodinger's equation. And Schrodinger properly thought of the electron in terms of a three-dimensional stationary wave or wave function represented by the Greek letter psi. So a few years later, Max Born, there are so many names that you would find the most common names in physics are Einstein, de Broglie, Heisenberg, Bohr, Born, Planck. So many scientists were working on quantum mechanics. And so Max Born's contribution was that electrons are still particles. And so the wave represented by psi are not physical waves, but instead are complex probability amplitudes. So what does that mean? It means that if you take the square of the wave function, it describes the probability of that particle being present near that location of space. So the wave function for a particle in an atom gives you the probability of where you're going to find that particle. So you only can know the probability, you can't know exactly where a particle is. So wave functions can be used to determine the distribution of the electron's density with respect to the nucleus. So in the general form, Heisenberg's equation looks like this. If you take physical chemistry, which is an upper level course I teach, you'd actually solve this equation, but it's a differential equation, which means it takes calculus, and we don't require calculus for Gen Chem, so we won't even really look at what this equation means, but that's the equation you would solve. So H is the Hamiltonian operator. It's a set of mathematical operations representing the total energy of the quantum particle. Psi is the wave function, E is the total energy of the particle. So Schrodinger's work, as well as that of Heisenberg and many other scientists following in their footsteps, is generally referred to as the development of quantum mechanics. So electrons in an atom can exist only in discrete energy levels, but not between them. So we want to start understanding what quantum theory tells us and what we know from experiment. The energy of an electron in an atom is quantized. So it can go in steps of energy, but it can't continuously add any quantity of energy. The energy can be equal only to certain specific values and can jump from one energy level to another, but not transition smoothly or stay between these lines. It's a lot like thinking if you were climbing, a mountain and you took the side that's a straight cliff, but there were ledges and you didn't have ropes. So you couldn't hang between two ledges, but you could be on a ledge, which would mean you'd have a discrete energy, but you couldn't hang in between. So you couldn't stay between those levels. So the principal quantum numbers, so now we're going to talk, there are 4 quantum numbers that describes pretty much that ledge. So if you're talking about going up the mountain, the quantum numbers are going to be labels you'd put on each of the ledges that you could sit on. The first one is labeled with an N. That's the principal quantum number. Its value can be 1, 2, 3. It's going to be an integer up to infinity. Generally speaking, the energy of an electron in an atom is greater for larger values of N. Excuse me. N is referred to as the principal quantum number or shell number. And the principal quantum number defines the location of the energy level and is similar in concept to the Bohr model. Yeah, so this is just a picture of that. So in the Bohr model, we knew as you increased energy, you were moving the electron further from the nucleus, and each of those levels was labeled with an N value, and that's what this is showing. You could stop at any of those orbits and you'd be in a different energy level, and its principal quantum number N would be different. Atomic orbitals. So the principal quantum number is one of the 3 quantum numbers used to characterize an orbital. An atomic orbital is a general region in an atom that an electron is most probable to reside. So when we look at the shapes of orbitals, we would know with a high probability that's where we'd find the electron if we measured its position over and over and over again. So an atomic orbital is distinct from an orbit. So doesn't mean that the electron is orbiting the nucleus at that radius. It simply means that you have a function, an atomic orbital, that gives you the probability of where you might find the electron. The quantum mechanical model specifies the probability of finding an electron in a three-dimensional space around the nucleus. So the next quantum number, so we had n, the next quantum number that we also need to put on our step, our ledge, to identify what its energy is called the angular momentum quantum number, L. And that's an integer that defines the shape of the orbital. So in class, we'll look, let me see if in a little while, we'll see pictures of them, but in class, I'll show you models of the orbital shapes. So L takes on the value 0, 1, 2, all the way up to n minus 1. So the L value depends on the n value you're in. For an orbital with n equals 1, that means L can only be 0. If n equals 2, it could be 0 or 1. So orbitals with the same value of L form a subshell. So if all this is totally new to you, think you're going to listen, you're going to come back, we're going to talk about it again in class, you're going to work problems. And through that process, I think you'll start to understand as well as figure out questions that you have. But right now, if it seems like there are just a lot of new words and concepts, try just to hang with it, knowing you're going to come back and work through it enough times that you will understand it, I hope. So instead of using numbers, the orbital or the angular momentum quantum number is often designated by letters. So if we say it's L equals 0, we call it an S orbital. 1 is a P orbital, 2 is a D, 3 is an F. And maybe you're familiar with that from Gen Chem in high school. So when we talk about these orbitals, I'm not going to ask you about nodes. And the important thing is just that a node is a place where you have 0 probability of finding an electron. And we'll look at them as we go through these slides, and I'll talk about kind of the philosophical meaning of that. But I won't ask you to identify number of nodes. So this goes through the number of nodes. We'll look at this in slides, but I won't ask you to use these equations. This shows the probability of finding an electron as a function of distance from the nucleus. So what you notice is that when you're in a 1s orbital, so it's n equals 1, L equals 0, you don't have any nodes. You just have a function that as you get further and further from the nucleus, the probability of finding an electron goes to 0. But when you get to a 2s, you have 2 humps. So there's a location at this first minimum where you'd have 0 probability of finding the electron. And that's why nodes are one of those philosophically challenging concepts in quantum mechanics. So that means if I measure where the electron is over and over and over when it's in a 2s orbital, I'll find it with the probability of this small hump in that region and the probability of the big hump in the region after the node, but you will never find it at the node. So it's as if it can be here and here, but it never can pass through and go from there to there. So I'm not going to once again ask you to identify the nodes, but just have a concept of why that's a very interesting idea. So the orbital shapes, we'll see these models in class. S is a sphere, P is a dumbbell, D and F are more complex. And these shapes represent the three-dimensional regions where the electron is likely to be found. So here are the pictures. We'll have physical models. So at the very top, that blue ball is an s orbital. It's spherical. And then the next row where you have 3 of them, they're dumbbells. So these are p orbitals. The next row is d orbitals. And then f orbitals, there are 7 of them. So it takes 2 rows, but you see they get much more complicated. So you want to think about those both red and blue lobes representing places where you would have a high probability of finding an electron if it was on a ledge that was labeled S, P, D, or F. So if an orbital has an angular momentum L doesn't equal 0, then this orbital can point in different directions. So if you think about that, that means when you're looking at the p orbitals, the second row here, they could be along the x-axis, it could be along the y-axis or the z-axis. So there are 3 of them. And each of those will have a different quantum number called the magnetic quantum number, and that specifies which orientation the orbital has. So the value of m sub l depends on the value of L. So if you notice, when you have s orbitals, there's only one orientation for that. So m sub l has only one value. But for the p orbitals, there are 3 possibilities for the orientation. So we're going to have 3 m sub l values. When you get to the d, there are 5 different orientations. So we're going to have 5 different m sub l's. So the rules for that is that m sub l goes from minus L up to plus L by integers, and it goes through 0. So that means you have all the negatives, the positives, and 0. So you have 2 times L plus 1 orbitals will have the same L value. So 1 s orbital for L equals 0, 3 p orbitals, because if L equals 1, you have 2 times 1 plus 1, 5 for the d orbitals, 7 for the s orbitals. So when referring to an orbital, usually both the n value and the letter designation for L are reported. So we call it a 2s orbital, a 2p. So once again, these are just ways to label those ledges that your electron's on, those energy steps that the electron can be on. So in the case of a hydrogen atom, energy of all the orbitals with the same n are the same. This is called degeneracy. And the energy levels with the same principal quantum number are called degenerate energy levels. However, in atoms with more than one electron, this degeneracy is eliminated by the fact that electrons interact with each other. And so orbitals that belong to different subshells have different energies. So when we go back here, a subshell, there's the S subshell, the P subshell, the D, the F. So a subshell is the set of orbitals in a shell where they all have the same L value. So yeah, orbitals with the same subshell are still, just wait. Yeah, they have different energies if they're a different subshell, and orbitals within the same subshell are still degenerate and have the same energy. And that's looking at this as an energy diagram. So the 1s orbital is the lowest in energy. And then the next ledges you could sit on would be a 2s. It's a little bit lower in energy than the 2p, which all have the same energy. So energy's on the y-axis. Then you jump up 3s, 3ps, the 3ds, the 4s. So the last quantum number we have to talk about doesn't come from quantum mechanics, but it's necessary, and we'll understand where it comes from here in a second. So the first 3 quantum numbers, the n, the L, and the m sub L, define the region of space where an electron is most likely to be located. The electron spin is a different kind of property, so this is going to be the last quantum number. Electron spin describes an intrinsic electron rotation or spinning. An electron can only spin in one of 2 quantized states. So the spin quantum number m sub s can either be plus 1/2 or minus 1/2. And an electron, regardless of the atomic orbital it's located in, can only have one of these 2 values for the spin quantum number. So this is just showing you what that means. So anytime a charged particle is moving, it creates a magnetic field. And so you could identify which spin it is, up or down, because when you allow that electron to interact with the magnetic field, its energy will be different, whether it's aligned with the field, so the field is the B0, or if it's anti the field on the right-hand side. So that spin quantum number leads to de Pauli's exclusion principle, which says an electron in an atom is completely described by 4 quantum numbers, n, L, m sub L, and m sub s. And Pauli formulated a general principle, the Pauli exclusion principle. No 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. It's as if you're saying each ledge, so each state that an electron can be in, only has room for 2 electrons. And those two electrons have to have opposite spin in order for them to sit on that same ledge. So electrons can share the same orbital, but only if they have different m sub L numbers. And since the spin quantum number can only have two values, no more than two electrons can occupy the same orbital. So that's saying if we had an orbital, let's say we're talking about a p orbital in the n equals 2 state, it would have n equals 2, it would have L equals 1, it could have m sub L of 0, plus 1, or minus 1. And as soon as you pick one of those, you've picked one of the orbitals. And then the last quantum number, m sub s, could be plus 1/2 for one of the electrons and minus 1/2 for the other. And that's it. Then there's no more room. So this is just a table summarizing the rules for the quantum numbers. And I think this is an important table maybe to put on a note card for a test, which we'll talk more about this in class and use it, but it's just a summary of the rules that we just went through. So we have one more section for today's material. We want to derive something called an electron configuration for an atom. We want to identify and explain exceptions to predicted electron configurations, and we want to relate electron configurations to element classifications in the periodic table. So the energy of atomic orbitals increases as the principal quantum number increases. That's the n. And as the principal quantum number n increases, the size of the orbital increases, and the electrons spend more time further from the nucleus. So that goes along with what we learned with the Bohr model. The further the electron is from the nucleus, the more energy it has. It's more stable and lower in energy if it's closer to the nucleus. So the attraction to the nucleus is weaker, and the energy associated with the orbital is higher. So in any atom with two or more electrons, the repulsion between the electrons makes energies of subshells with different values of L different. So the energy of the orbitals increase with a shell in the order SPDF, and electrons and atoms tend to fill low energy orbits first. So yeah, this is just showing you the relative energies, which you can also get this concept just using the periodic table. So it's not too important to understand this, but you might want to come back and look at it after you look at the periodic table and what we know about energy differences for the orbitals. So the arrangement of electrons in the orbitals of an atom is called the electron configuration of the atom. An electron configuration consists of symbols that contain three pieces of information: the principal quantum number n, the letter that designates the orbital type L, and a superscript that designates the number of electrons in that particular subshell. So for example, for hydrogen, it has one electron. The lowest energy orbital is the 1s on this picture. So that's where it will be. So the 1 indicates n equals 1, the s indicates L equals 0, and the superscript 1 means that hydrogen just has one electron in that orbital. So to determine the electron configuration for an atom, we add a number of electrons equal to its atomic number. Beginning with hydrogen and continuing across the periods of the periodic table, we add one electron to the subshell of lowest available energy. And this procedure is called the Aufbau principle, from the German name Aufbau, to build up. So to build up from the lowest energy to wherever you have to be, depending on how many electrons you have. So when writing electron configurations and orbital diagrams, keep in mind the Pauli exclusion principle. We'll see what that means. So this is just a picture that shows you the orbital filling, the order in which orbitals fill. So we'll also talk more about this in class, but 1s fills, go back up here, then 2s, go back up here, 2p, 3s, 3p, 4s, 3d, 4p, 5s. So you go down the diagonal from right to left, and then you go back to the start on the right of the end of the arrow, down to the pointed side of the arrow. So this is just a picture of the periodic table, and it shows you what I meant when I said that this picture really you can figure out from the periodic table, because it shows you that the shape of the periodic table is dependent on that filling pattern. So the first two columns, electrons are always going into s orbitals. So 1s, 2s, bigger s orbital as you go down the periodic table. And then as you go across the middle region, they're filling d orbitals. On the far right, they're filling p orbitals. And we'll see in a second that we have an extension at the bottom for where they go into f orbitals. So orbital diagrams are pictures to represent the electron configuration, showing the individual orbitals and the pairing arrangements of atoms. So you could go hydrogen is a 1s1 electron configuration, and you could then represent that 1s orbital and put one arrow in it, meaning that you have only one electron in there. So helium would be similar, except you have two. You have one electron with a +1/2 spin and one with a -1/2. Lithium has the 1s filled and then the 2s with one in it. So this is just a way to represent the electron configuration. Sometimes orbital filling diagrams give you more information when we talk about things like whether or not something's magnetic. That will be helpful. Here's another one for boron. And then we get to one more rule. So we had the Pauli's exclusion principle that said no two electrons can have the same 4 quantum numbers in the same atom. Hund's rule says that the lowest energy configuration for an atom with electrons within a set of degenerate orbitals is that having the maximum number of unpaired electrons. So if you need to put 2 electrons on the bottom here for carbon into the 2p subshell, one's going to go into each individual orbital first before you start pairing them. That means we'll have 2 unpaired electrons. Anytime you put a second electron in the same orbital, you pair the spin, you have a +1/2 and a -1/2, which cancel each other. So these are just showing you that Hund's rule. So then when you went from carbon to nitrogen, you'd have all 3 of those 2p orbitals with 1 electron. You get to oxygen, you have to start pairing one up. Fluorine pairs a second one, and neon pairs all 3 of them. So that's showing you how the electrons go into the orbitals based on Hund's rule. So valence and core electrons. Electrons occupying the orbitals in the outermost shell are called valence electrons, and the electrons occupying the inner shell orbitals are called core electrons. The core electrons represent the Nobel gas electron configurations, and electron configurations can be expressed in an abbreviated format by writing the Nobel gas that matches the core electron configuration along with the valence electrons. So if you're talking about sodium, when you get over to a 2p6, that means you've filled that entire n equals 1 and n equals 2 shell. So those are the core electrons, and then guess I'd call it tan square for the 3s1 is the valence electron. So you can abbreviate that as neon, because neon is a 1s2, 2s2, 2p6, and then the outer electrons, the 3s1. And it's abbreviated so easier to write, but it also gives you some information. It reminds you that there's only 1 electron in sodium that's very reactive. As soon as you fill an inner shell, that's a very stable thing, and you're not going to take electrons out of it. So these are just some abbreviated electron configurations, and it shows you why the periodic table has the shape it does. So lithium, sodium, and potassium are all in group 1. So a group is a column, and this shows you why that's true, because they all have the same number of valence electron in the same type of orbital. So lithium has a 2s1 valence, sodium has a 3s1, potassium has a 4s1. Therefore, they're going to have similar chemical reactivity, so they're in the same group. Same will be true if you compare this group 2 to the periodic table. They're just 1 over from group 1, so you'll be able to see that they're going to have the same valence, except there's an extra electron. So that's a picture of that. Oh, and this finally has the F's in it. So Those two green rows at the bottom are only at the bottom because if they weren't, the periodic table would be so wide, you'd have to roll it up. Because if you notice, when you're looking from barium to lanthanum, goes 56, 57. But then when you go from lanthanum to HF, which I'm sorry, I don't know the name of, there's a big break. You go from atomic number 57 to 72. So that's where you would insert this first row. So it goes from 58 over to 71. So that's where the F orbitals are filling. So that's just showing you a more complete periodic table. So beginning with the transition metal scandium, additional electrons are added successively to the 3d orbital. Yeah, so that's in the first D series. D subshells are filled to capacity with 10 electrons because there are 5 of them and each orbital can have 2. And after the 3D is filled, electrons are next added to the 4p. So when you're looking across the 4th period, the 4 purple 4 on the left-hand side, you're going to fill the S's, then you're going to fill the 3Ds, and then you're going to go back and fill the 4Ps from gallium over to krypton. For the 2 periods of inner transition metals, so those are the 2 Fs at the bottom, electrons are added to an F subshell. F subshells, there are 7 orbitals, therefore it takes 14 electrons. So these 2 green rows are each 14 long because you're filling F orbitals. So now when we look at some exceptions to how you fill and how you get electron configurations, examples of copper and chromium, there's something stable associated with either a half-filled or a full-filled D subshell. So an electron shifts from the 4s into the 3d subshell to achieve this stability. So what you would expect for copper is a 4s2, 3d10, or 3d9, but because a full D subshell is stable, it's actually going to be a 4s1, 3d10. So look at the chromium. You're going to go from a 4s2 that you'd expect, 3d4, to one of those S's going into the D so that you have both a half-filled S and a half-filled D. So let's just look at copper and chromium here. So copper is in the 11th period. So if you looked at it, it should be a 4s2, 3D, we're over 9, so it should be 3d9, but it shows it here as that anomaly. It's a 4s1, 3d10 because filling that D subshell is more stable. That is just showing you the electron configuration for phosphorus. And this is where we're going to stop, I think. Yeah. I feel like this is a new section. Electron configurations in the periodic table. Maybe not, but I think I'm still going to stop there because that's about as long as I can talk without taking a break. So we'll come back and finish the chapter.